So I apologize for that. So hopefully that won't cause too much problems because it's a 1 hour lecture. And unfortunately, there's no way to recover it. So anyway, hopefully it wasn't too big of a deal. Back to hash functions. So we talked about hash functions, secure hash functions. Okay? And we're going to look at it in a more rigorous way. A hash function is a function that does both a compression and some computation, high-speed computation. Okay? And I said that usually the hash functions do not require a secret key. We can definitely design a hash function that has two inputs. One of them is the message, the other is the secret key. But it turns out that it's not necessary because we have a standard to convert a non-keyed hash function into a keyed hash function. So that is why we actually don't need to design two separate hash functions. One is unkeyed, the other is keyed. There's no need to do that. And we're going to look at these hash functions in a little more detail. Number one, we want to define what's one-wayness. Okay, so the one way is this is one of the most important property of hash function, one-wayness. So this can be rigorously defined as follows. Okay. Given any hash value, so given any y, right, given any value, it is computationally infeasible to find an x that hashes to y. Okay, so that is okay. Now, we want also formally define the collision resistance properties of hash functions. Okay, we want to kind of theoretically study the invertibility of a function as an analogy. Okay, so what we're doing here is we know that hash functions, they are by themselves invertible because they are it's many to one because it does compression. So you really cannot talk about invertibility. There's no way a hash function can be inverted, but we want this type of hash functions to be secure. So that is why we define the collision resistance properties. And there are two ways to define it. One of them is what's called weak collision resistance. The other is strong collision resistance. Let's take a look, okay? Because we have to distinguish between these two cases because later when we talk about birthday attacks, that's important. So we gotta understand in detail. Let's take a look. Given any x, okay, it is computationally infeasible to find another one that collides with x. By colliding, we mean two different values that hashes to the same value. So we have x and then have x prime, right? And then we apply this hash function. Okay, we get hx. Okay? If this happens, if two values, after putting those values to the hash function h, if they are identical, we call this a collision. So this is a collision. So weak collision resistance basically means give me one of them. It is computationally impossible to find another one that collides with it. That's called weak collision resistant. Strong collision resistant. Okay. The definition is it is computationally infeasible to find anything without any restrictions at all. If you just look at the definitions, you may not be clear why this is strong, why this is weak. And it takes some time to digest. Actually, this one this one, you give me some x. So you already give me more information. So if you give me this information, okay, then you cannot find the other. So you give me more information. If this property holds, then this is a weaker version. Okay, the stronger version is you don't give me anything at all. We just said it's impossible to find such thing, no matter you give me this or not. Okay, so that is why the strong implies the weak, but not vice versa. Okay, it's not very obvious, right? Not very obvious. Maybe we can think about it this way. Yeah. Okay, so let's see. We have strong collision resistance. We assume that, and then we can prove the weaker version is also true. Okay, so the stronger version says we cannot find anything whatsoever, any collision at all, computationally. So that's a strong version. Weak collision, you give me x. So suppose we already have the strong collision resistance, and then you give me some x. Is it possible? Is it computationally feasible to find another one that collides with it? No, because you cannot find anything whatsoever without or with any information at all. So obviously strong implies weak. The weak does not imply strong. And there's a huge difference too. And later we will talk about that. Later we'll talk about it, because this actually is a critical, it's a critical property, because when we talk about the birthday attack, later I will see that. So birthday attack, or sometimes it's called birthday paradox. Okay? It says you cannot find anyone with whose birthday is the same as myself. Okay? So that's the weak version. I already singled out myself, so my birthday is this day, and then I look at the students. It's difficult to find anyone that shares the same birthday with me. So that's the weaker version. The stronger version is you're actually trying to find anybody within this class, in the classroom, that has same birthday. So this one has less restriction, and this one has more restriction. And then later we'll quantify that, and then we'll realize that actually the probability that a collision happens the difference is huge. Okay, the difference is huge. Okay. So that's this. So strong and weak. So strong collision resistance implies weak collision resistance. The other thing is collision resistance is a different idea from the one-wayness. We can take a look at this. Okay. Does strong collision resistance imply one-wayness? The answer is no, because we can make an artificial example that actually shows that it's not this case. Let's take a look at this. First, let G be a collision resistant function. So this is G. G maps in any string of arbitrary length to an n fixed length, which is of length n, okay, binary string. Suppose we already have that, so this is G, and then we're going to construct an artificial example. We're going to construct another hash function, which is not one way, but it preserves the collision resistance property. So let's define artificial function hx. So the hx consists of two parts. Number one is sometimes it simply applies g. In other cases, it doesn't apply anything. So if x is n bit long, okay, we don't do anything. We just concatenate x, append x at the end of 1, okay? And then in this case, okay, if it's not n bit, less than n bit or more than n bits, then it is 0 and then appended with gx. We look at this case. Okay. This still preserves the collision resistant properties, because you cannot find any collision in either case. If it's in this case, it's related to G. you cannot find any collision because G is collision resistant. And then here, it's a one-to-one mapping. So there's no collision at all. So no collision in this case. However, it is not one way because here, this part is reversible. Even though there's no collision, it is invertible. So that's the problem. So this example shows us that the collision resistance and one-wayness are two separate ideas. They're totally independent of each other. This diagram shows the hash function with digital signature. This is the digital signature of the appendix type. Obviously, for the message recovery, we don't use any hash because for message recovery type, you have to recover the message. Okay? And then if you apply hash, you cannot recover because it has compression. It's a many-to-one mapping. That is why it's only used in the appendix. So you have a message, okay? And then this message goes directly here. It's plain text, okay? And then the plain text will be attached with the hash, with a message authentication code, which is obtained like this. First, you enter the hash function. This is a hash, and then you sign it with your private key and concatenate. So this is the message authentication part, your signature. Okay, and this can be verified by checking by calculating the hash again, and then take this part to do the to apply the verification function using the public key and compare whether or not they are equal. So if anything is tampered with, for example, the messages has been tampered with, then you cannot be verified. The verification algorithm will give you a no. Or if the signature has been tampered with, in that case, you apply you feed in the public key, you cannot be verified. Then you also give you a no. The verification algorithm will also give you a no. Okay. So basically, the use of hash functions are to detect any changes to the message. So that is why I said in the beginning, compare message without information leaking. Yeah. So that is useful when we use the digital signature. Okay. Now let's take a look at the birthday attack. Sometimes it's called the birthday paradox. But anyway, this is actually a misnomer because it's not a paradox. There are a lot of misnomers. Birthday paradox. Why is it a paradox? I don't know. Let's take a look. Suppose there are 13 people in the class. Maybe we have 13 people. Okay. The probability that somebody share the same birthday with myself, with me, is 3.5%. So it's low. Okay, it's low. Suppose there are 13 people. If there are more people, then this probability will be a little higher. It will be higher. So that's the this corresponds to the weak collision resistant property. Yeah, somebody shares the birthday with me, and the probability is this, not too high. Right? If you calculate the property that at least 2 students share the same birthday, it's much higher. It's 19.2%. It's almost 20%. So why is it called a paradox? So maybe I don't think it is a paradox. It's just calculating the probability. Why is it a paradox? Maybe some people think this is a surprise that really the probability that 2 people share the same birthday is way too high. It's beyond imagination. So maybe it's a paradox. Maybe somebody share a birthday with a fixed person is so low. So it's maybe because of that. Anyway, there's a significant difference between these 2 cases. that's one of the reasons why I said this is quite important in designing hash. Actually, in deciding how long the hash value has, what is the length of the targeted hash value? It depends on this. Okay, so it does play an important role, because for ordinary length, the length that we normally use to design symmetric algorithms, it's not enough. It has to be doubled. That's because of this. So we'll analyze that a little bit. It's not too difficult. It's high school math, so it should be okay. Let's take a look. So suppose there are n students, okay, in the class. Okay. Let's talk about a birthday attack. Okay. There are n students in the class, and then we're talking about probability that two students share the same birthday. So the birthday, number of days in a year, suppose 365. And then we calculate this probability. So it's high school math. It's just, when we calculate this type of probabilities, we gotta be very, very careful that we don't count extra stuff, and then we have to be careful that we don't count anything twice. Okay, and then it's also very careful that we don't omit anything. That's the hard part. The calculation is actually very straightforward. It's easy to make these mistakes, so we go very slowly. Let's take a look. This probability, at least two students have the same birthday. So this probability is 1 minus this probability. Everybody has different birthdays. Okay, we go very slow. Let's take a look at what this probability is. Everybody has different birthdays, and then there are n students in the class. Okay. To make this happen, maybe we can take each student's birthday as a random variable. Okay. And then I just randomly choose one. Let's pick the first student. The goal is not to overlap with any other students' birthdays. So the first student I pick, that's 1. I have no restrictions at all. So that's 1. 1 is the probability. And then the second student I pick, I have to avoid overlapping with the students that I have previously chosen, so which is 1 student. So I have to avoid that. So we have 1 less day. So that is 1 minus h, 1 over h. So that's the second students I pick. Third students I pick, I have to avoid 2 students. And so on and so forth until the last students, in which I have to avoid previous n minus 1 students' birthdays. So this is n minus 1. Okay, that's the probability. Now, there's no direct calculation we can do to derive useful results. So we have to use some estimation. Okay, so we sacrifice something. We use inequality instead of equality. Okay, so let's sacrifice this. Now, we use this things, something like similar to the binomial expansion. So the binomial expansion is, you guys know, like if you have something like this, and then if this x is very small, okay, then what happens is we have, according to the binomial expansion, okay, we have 1 to the power of k plus, okay, we have this, k1 x k2 square. Something like that. This expansion tells us that if this x is very small, okay, if it's very small, then the square will be like really small compared to the linear term, because let's say your x is something like this. When you do a square, it actually becomes this, right? So this is they are at different order. So this is much smaller than this one. So the square and then the third and all these higher terms are all very small. Like If the x is small enough, then these can be omitted, pretty much omitted. So this is the major term. The linear term is the major term. Okay. So in that case, this is actually kx. This is kx. So we can almost just consider the linear case. The k is here. Okay, that's the k. And then this also works if, it also works when we have a negative sign. So if we have a negative sign here, we just change the sign. Just change the sign. And then we have higher order terms on the right. They are all very small. Okay? So that's the reason why here. Okay, here. If we can regard this minus 2, okay, as a linear term. This is linear term. We can actually pull out this one, the linear. We'll pull out this number to the, to the index level. So this is the index level. And then they're also very simple. And then actually it is an inequality. So we can pull this out. The thing is, if we pull this out, then these parentheses, they will be the same. And then they're manageable. Otherwise, there's no other way of calculation that can help us derive useful results. Okay. So we pull this out, and then they're all the same. And then we collect those terms. Now it becomes this. Okay. So this is the probability. Okay. And then we're using another inequality. Okay. So here, now what we want to do is we want to use this. If you guys know the natural exponent in like elementary calculus, we have that. So what's the natural exponent? So this number, right? Something like that. So this is the natural number, and then how do we get it? There's one formula. It's this. Something like this. Something like this. So here is, we have two competing forces. This delta x is approaching 0. So there are two competing forces within the parenthesis. This approaches 1. This is slightly bigger than 1, but it approaches 1. Okay. And then here, the exponent is pretty big. So the exponent is increasing. So we have two competing forces. Now we have we have a number and then its exponent. Okay. If the number is 1, then the exponent, it doesn't matter what the exponent is. The result is 1. Okay. However, if this number is not 1, if it's even just slightly bigger, right? And then if the exponent is very big, okay, then this will go to infinity. You approach infinity. So if the exponent is increasing, then this whole thing is increasing. But if this delta x is approaching 0, then this exponent has, it doesn't matter what it is. It is 1. So these two forces are competing. So this, if it goes more towards 0, then it doesn't matter. This approaches 1. Okay. If this goes to 0, then this goes to 1. However, if this goes to 0 at the index level, it goes to infinity. So two forces are competing with each other. So finally, they have to balance. In this formula, they balance in a way that they actually balance right at this natural exponent. Yeah. So that's the E. The E. That's the definition. So this happens in many cases in nature. A lot of, you have two competing forces. One is at the index level, the other is at the base level. They're competing with each other. Finally, they have to agree on something. So this gives us a formula about two competing forces, and then where will they agree? So from here, we want to choose them in a way that they look like the same. So this is the case when we have a plus sign. With a minus sign, that also work. Okay, so if it's a minus sign, if it's a minus sign, this is also a minus sign. So this minus sign, we can actually hold it here. Yeah, this also works. Okay, so here we have this 1 over h, and then we choose it. We make it this way. Okay, we make it this way. So we have an h here. Okay. So we have a minus sign. If this is exponent, right? If this is natural exponent, then we know that this minus sign is actually it's a reciprocal of this number. So actually, this corresponds to this case. This case. Because of this minus sign, this e on the right becomes 1 over e. Okay. So that's this case. Now we make here we have an h here. So what we want is we want to create an h on the index level. We'll create an h, and then we have to respect this equality, so we have corresponding terms to cancel that. Okay, and then this part becomes e. Okay, and this part becomes the reciprocal of e inverse. So altogether, they are actually close to this part. Okay, so that's the birthday attack. So the probability is similar to, is approaching this. It's approximately this number. Okay. Now, if we think of it conversely, now what we want to do is we want to decide how many bits do we need for this h. Okay. So conversely, here is that given the number of students and number of days, we want to calculate the probability. Now we do it conversely. Give me the probability, okay, in advance. Okay, what is the number of students such that the collision happened with roughly this probability? So that's the question. It's a reverse question. So what do we do then? Is that we wish to make this happen, right? So give me the probability. So P E equals this. Okay, so P. Give me the probability P. We want to determine N such that this happens. Right? So give me the probability. Now, so probably the probability is P. Now we kind of solve this equation, right? So we move this e to the left, and then move p to the right, and then we get this. Right. And then we can take the log. We can take the natural log. If we take the natural log, then we get the index. So on the left, so we take the natural log on both sides. Then we get, okay, this. This is what we get. Okay. And then we move this side to the right, then the natural log becomes here. It becomes the natural log of 1 over 1 minus p. Okay, so we can roughly solve this n. So the n is roughly this, 2h, and then this value, Okay, so that is this value. Okay. And then, so roughly speaking, this
this n is at the order of big O h square root. Square root is here. Okay. Now, this is the case where there's no restriction at all, kind of like a strong collision resistance case. Now, we want to compare with the other case, the weak collision resistant version. We want to make a collision happen with a fixed string, with somebody. Okay, so what is a fixed string? That means the probability that somebody shares a birthday with me. So what's the probability? Okay. Suppose there are 13 people. They share the same birthday with me. So the probability is this. The probability that somebody shares the same birthday with me is here. It is this. Suppose there are n students. If there are n students, the probability that somebody shares the same birthday, somebody collides with me, is this, right? Give me the P, right? Give me the collision. Somebody share the same birthday with me. The probability is this. Okay, so if we want to, so let's organize this a little bit. We move this P to the left, and then we move this to the right. Now it becomes this. Okay, and then using this same way of manipulation, this is roughly exponential from this exponent. This is roughly this number, OH, so big OH. Okay. So there's a difference. In this case, the weak collision resistant, the H, the order is linear to H. In this case, the order is the square root of H. So where does the square root come from? Actually, the square root comes from n squared. That's a reason, right? And then here we don't have that square. So this is the reason why we have square root of H. Okay. And then this square comes from here, because we're summing these indices. That is why we get this square, right? This indices. We sum 1, 2, 3, 4, and a sum up to n minus 1. So we have roughly n squared. That is why we have this is square. And then that square becomes the square root here of a big O. Square root of H. Okay, so that's a birthday attack. So roughly speaking, let's see if we want to achieve the same level of security. For the weak case, suppose we need the hash, the hash length, some hash length. And then for here, for the stronger case, if we want to achieve the same level of security, that length has to be doubled to counterbalance the square root. That's the idea. Generally speaking, at the moment of designing designing those hash algorithms, at that moment, the symmetric encryption algorithms that are usually used to achieve a certain level of security that is roughly like 64 bits, 128 bits. For 64 bits, let's take DES, for example. It's a little less than 64. It's like 56 bits. But to achieve the same level of security, if you want your hash function to be collision resistant and the level of security is similar, you probably have to double the length. So it's like at least 128. Okay, so 40 years ago, 30, 40 years ago, at that moment we have DES and also other encryption functions like IDEA and those functions. They're generally speaking, their level of security is about 64 bits. Okay, that's 30, 40 years ago. Now it's 128 bits because we're using AES right now. But if you want to achieve the same level of security, in hash, you have to double that. for the reason I just explained. That's why we need 256 bits hash. Okay, so that's the hash. That's the hash algorithm we use. 256, SHA-256. Actually, now most cryptocurrencies use this. For example, like the Bitcoin, their hash value used is SHA-256. That's because of this. So 64-bit hash is not secure. Actually, the 64-bit was chosen at the time that encryption algorithms were designed, and in that time, with that computation power, it takes like 1,000 to 5,000 years to topple the system. So that time, people use a lot of 64-bit stuff, encryption algorithm. So the hash is 64 bits. So the birthday attack versus the hash function. Actually, the result is quite easy to formulate this result. Okay? So you just double the length, whatever the length you need. That's it. Yeah. We need to use larger message authentication code by doubling the math of the encryption algorithm. Okay. We can also use some block ciphers as hash functions as well. We can use block ciphers. For example, we can use the CBC. If you guys, I think probably most students already forgot what CBC is. Let me take a look. CBC, yeah, just to kind of remind you guys. CBC. Let's take a look at this. The CBC. Long time ago when we talked about the symmetric algorithms. So those block ciphers, they only work with blocks. If we have a large piece of data, how do we apply those? And there are many modes, right? The CBC mode is one of them. So the CBC mode is actually, it can be regarded as a hash as well. You can use, so you have an input, right? Like this. Just think about it. If the input is the same as plain text, we just take the last block as a hash. That works as well. It also works as message digestion because your output is always fixed length and then your input is arbitrary length. So actually you can use this. Okay, you can use any encryption function and then you use the last block. Use the last block as a hashed value. So that also works as well. CBC mode. So for example, you can use the initial vector as a 0 and then use 0 pad the final block and then you compute this. This can be CBC, but you need to have a key, right? So such thing cannot be used as an ordinary hash function because it needs a key. However, it can be used as a message authentication code because message authentication code we would basically need a key. It's a key to hash. So in that case, it works. But you cannot use that as general hash functions. Okay. So you can use that as message authentication code. However, the hash is a little too small because roughly we have to double that for the paradox, for the birthday paradox. Due to the birthday paradox, the hash value is too small. So probably you need to use AES, right, for this case. Or probably you need to use like 256-bit AES, that kind of thing. Okay. Hash algorithms. The design of these hash algorithms are very similar to the design of encryption algorithms. Okay? But there are some differences. first, we don't need to have a key. Okay, and then the other thing is we don't need to be able to reverse every step. It does not need to be reversible. Okay. And still, there are still they share a lot of similarities, but it doesn't have to be reversible. Actually, that gives us more freedom to use other arithmetic operations, and then we can also use easier operations as well. Okay. Message authentication. Let's take a look at message authentication that I said. Message authentication code. That gives us data integrity and the validating the identity of the originator. So this can be achieved by applying a hash and any algorithm with an input of a secret key, okay, which can be a signature, because signature needs a secret key, or a symmetric algorithm as well. Okay. A symmetric algorithm, in that case, you cannot verify. It's encrypted, right? Let's say you use an encrypted algorithm, like AES, for example, and then in that case, not everybody can actually see the message. Only you and the person only you and the sender. Okay. But that also gives us gives us validation of the originator. Okay. The only difference is that you cannot have the non-repudiation. In that case, it's absolutely necessary to use asymmetric crypto systems. Okay. So message authentication via message encryption can be used. Okay. Message encryption also provides a measure of authentication. You can use any symmetric encryption algorithms, AES, anything. Well, that gives us validation of the sender and confidentiality as well. Even though the confidentiality is not absolutely needed, we can still achieve that. Okay. So this is general message authentication code. Okay, using signature. Okay, we use a hash and apply a append message as signature. Okay, we've already seen this one. This diagram I already explained. There are some advantages. Okay, it provides validation of the sender. Okay, and then there's no encryption because it's appended at the end of the plaintext. Okay, so sometimes only validation of the sender is needed. You don't have to do encryption at all. Okay. And the good thing is also if you use asymmetric crypto systems, it provides non-repudiation. And I already mentioned that. Okay. Okay, let's take a look at the message authentication code properties. So a MAC is a cryptographic checksum. We can regard it as this thing. Okay. For those who have already learned networking, computer networks, you know what checksums are, because transmissions, sometimes there will be errors. Sometimes some bits may be flipped. Okay, so you need to have a checksum to see whether there's any error in the message. That's error detection. So a MAC is kind of like that checksum, but with a cryptographic one. So you have a encryption of a secret key. It's cryptographic checksum, not just checking whether or not it's been altered. It also gives you the validity. Okay, so using a secret key K to condense a message, okay, from any arbitrary length to a fixed size. So it's a many-to-one function. Okay. And then it gives you good properties. So these are the requirements. Knowing the message and its MAC, it's computationally infeasible to find another message with the same MAC. So in other words, weak collision resistant. Okay. And also this MAC should be uniformly distributed. It shouldn't favor any particular bits or bit strings. Okay. So MAC also should depend on every bit of the message. Okay. And then DES CBC was the older version. CBC, cyber blockchaining, I just mentioned. DES CBC. That's the older version. It's not used anymore because the link is too small. IV0, set IV0, and the 0 pad final black. Okay. The final mag is too small for security because of the birthday attack I just mentioned earlier. Okay. And also non-repudiation cannot hold because it's symmetric algorithm. Okay. So using public key encryption, we can achieve both the validation and non-repudiation. Okay. So we can sign that using a signature to sign that. Okay. Now, we already know what the signature algorithms are. We learned RSA, we learned Elgamal signature, DSA, and also Rabin signature, 4 signature algorithms. Okay. Now, the only missing link is a hash function. Let's take a look at hash function. So this was the most popular one called MD5. And this was designed by Ron Rivest. Okay, Ron Rivest. Okay. It produces a 128-bit hash value. This was the older version, so the security level corresponds to the 64-bit message encryption algorithms. So this is designed by Ron Rivest, and then it was the most widely used hash function until 2004, until 18 years ago. Okay, so let's take a look at this algorithm. This was not used anymore, but it kind of gave us the basic ideas of how hash functions are designed. Maybe I can comment a little bit more on hash functions later when we talk about blockchain. Yeah, I will add some hash algorithm, like latest hash algorithm. So MD5. Let's take a look at MD5. We don't get into the really detail because they're quite similar. It's quite similar to symmetric encryption algorithms. We only look at some differences. Okay, so the message is like this. Okay? And then we have chop them into blocks, and then each block feed into MD5. So we digest each block one by one. Okay, so this way we can do message digestion. By the way, the MD5 stands for message digestion. This term was coined by Ron Rivest. Digest, like you eat something and you digest. When you digest, you output. And your output will be received by the input of the next block. And you keep doing that. And finally, you have a message digest, 128 bits. So that's MD5. And this is the 5th version, MD5. And then he thought it was good enough. So that's the. Let's take a break. Okay, let's take a look at this MD5. Okay. So the building block is this HMD5 in each round. And it consists of these functions. There's a function called G, okay, G function. And then the input is, the input is A, B, C, D. They refer to the 4 words of the buffer. They are stored as a buffer, okay, in varying permutations. Okay, the details are not important, just to show you guys. The key is that there's a highly nonlinear function called small g. Okay, small g. Okay, and then there are 2 arrays xk, okay, and then t. These are constant value derived from the sine function. Okay, and this small g varies depending on the 4 different depending on different round, there can be either one of the functions, big F, big G, big H, and big I. Okay, and then here, this A, B, C, D are the four words of the buffer here, A and B and C and D, four words. Okay. So B, C, D will enter this is a small g function. This small g function can be one of the four functions, big F, big G, big H, and big I. So let's take a look at this is big F. So we have an AND operation, okay? And then we have an OR operation. Here we have a negation and AND. These are logical operations. Big, this is bitwise OR, logical. I'm sorry, these are bitwise operations. Bitwise AND, bitwise OR, and negation. Okay. So it's a combination of those. And here we have an XOR, these bitwise operations. Bitwise operations. So they are very fast compared to other symmetrical algorithms. Encryption algorithms, they are very fast. And then either of the one functions will be this small g, and then you take these three values from the buffer, and then enter here, and then XOR with A, okay, and then XOR with these two arrays, and then circular left shift. You know, the tricks are like that. So this is basically MD5, one round of MD5. You just keep doing that, okay. And then generally speaking, it's the Ron Rivas designed it, and then he thought it's okay, and then indeed it was really okay until 2004. Okay, so 2004 was I told you there's a professor at Shandong University, 山东大学叫做王晓云. So at that moment, nobody knows who she is because she was a professor at Shandong University. Shandong University wasn't one of the most prestigious universities in China. No, you know, with the best universities, we have 北京大学然后清华大学、北京大学，对不对 ？The next one maybe 浙江大学中国科学院山东大学其实不要说前10绝对排不到，前20都可能有点问题成绩还 OK， 山东大学只能算是个地区性的。So it wasn't the top universities, okay? 所谓重点大学，它应该是在边缘可能在最后，好像还没被我不知道有没有列为重点大学。总之不是一个特别好的。Anyway, she was focusing on number theory in the math department of Shandong University. So nobody know who she is. And then she turned out to be, she started to doing research on hash functions starting from 2003. And then she found that if you use this type of stuff, okay, there is a way to create collision. In some cases, not in all cases, but in some cases, it's possible to create collision. Okay. So he wrote a paper regarding that, and then he submit to one of the most prestigious security conference called Computer Security, Communications and Computer Security, CCS. Actually, in our last month, I'll be giving you guys papers from this conference this year. Okay, so that's kind of like the most up-to-date papers, and then you guys can search any topics, any topic you guys are interested in. Okay. It can be theoretical, can be really application, that kind of stuff. Actually, she published a paper here, so she submitted a paper to CCS. And then what happened was CCS, this conference, the reviewer couldn't understand her English because her English was so poor that nobody understands. But you know, the reviewer found that if if there's some weakness in MD5, then that would be a big news, because MD5 was widely used in every online transaction. That was an old standard, so it's a big deal. So then the conference organizer actually specially arranged a person and a person to correct her English, editing her research paper. This hasn't occurred any time in the conference history, hasn't occurred before 啊，这英文太差了，结果 conference 的那 conference 的那个主持群们，他们找一个帮他特别改英文，改到大家起码可以看得懂，要不然他实在看不懂他在写什么。结果最后就是看懂了，然后大家看懂了之后呢，然后他就在2004的那个 CCS 他就 present 这不好像04吧，对 present 就是造成一阵轰动，后来呢后来结果北京的清华大学就请他去当教授了，然后他带了一个博士班，那个博士班大概10几个 PhD 专门在研究 hash。So actually, she then went to Beijing, Tsinghua University, in Beijing. So she's leading a team of more than 10 PhD students researching on this area. Okay. So she found that there's some weakness. And then there's another one called secure hash algorithm. It's called SHA-1. Okay. It produces 160-bit hash values. Okay. It's also preferred, generally preferred. We can take a look at the design. The design is very similar to MD5, but it's an improved version. So instead of 4 words, A, B, C, D, now they have A, B, C, D, E. Okay, and then here we have like circular shift, that kind of thing, and then here we have a similar thing. It's just a different way to put things together. And then we have this FT functions as well. This FT function can be one of them, several functions, several candidates of a function, which is a combination of bitwise operations, bitwise and bitwise or, negation, that kind of thing, bitwise negation. So it's very similar. So it's very similar to MD5. It was cracked by Wang Xiaoyun in 2005. Yeah, 1 year later, SHA-1 was not good. And then there's another algorithm called reversed secure hash algorithm. There's a European version called RIPE-MD. Okay. And anyway, this wasn't one of the this wasn't used widely. Now people are just using SHA with longer hash values. So there is SHA-2, the original SHA-1. SHA-1 produces 160 bits. Then we have SHA-2. Okay, SHA-2. Yeah. So SHA-2 is actually SHA-2 produces 256 bits. So SHA-2 is sometimes called SHA-256. This was currently used by many operations. Okay. So at this moment, the weakest link of a crypto system actually is in the hash function. Hash algorithm is the weakest. Signature, key distribution, these are all okay, but the problem lies in hash functions. So far, there's no good way of avoiding this problem. What they do is they increase the size. They increase the size of the secure hash functions. Okay, that's it. No good solutions. So far, even the latest cryptocurrencies, a lot of them, they're well, they're using different they're using different hash functions. Okay, and I would also cover some of them when we talk about blockchain later. Okay, later. So anyway, this is just the weakest link. This is RipeMD 160, and see, RipeMD is also very similar. So it was cracked as well, yeah, unfortunately. Yeah. So that's okay. So let's talk about this one, keyed hash. Keyed hash. So our final topic is keyed hash. The keyed hash is creating a message authentication code using a hash function. The hash function does not have a key to, does not have an input for key. Okay, so there are ways to somehow mixing the key with the input. The most naive way is this. This is the most naive way. You simply put the key here and then concatenate it with the messages. This is a way, right? Obviously, there's some. This is not. It's not that good. There's some weakness, because the key, and then the messages. We know that they have different patterns. Okay, and then some, and then. And then we know that the hash they process block by block. So here is like you can pretty much analyze the first few blocks. That's kind of like putting the key along in a hash function. So there's some weakness. So it's not satisfactory. There are other better ways to do that. Let's take a look at what the best way is. The best way is called HMAC. This is HMAC. That's it. One line. Okay. It's a nested hash function. Actually, the function, the hash is used twice. Maybe we can take a look at the diagram. It would be easier to understand. So there will be two fixed strings for padding. Kind of like the initial vector. So one of them is in the inner round. The other is in the outer round. So the outer round is called OPAD, 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 outer padding. And then the inner round is called IPAD. Okay, so let's take a look. First, we have this, this is the key, right? The key is concatenated with the IPAD enters here. With your message, okay, so it enters the hash first, the inner circle of the hash, okay, and then your key, and then do the actually XOR. Yeah, here the key is XORed. Key is XORed with IPAD first, okay, concatenated with the message, and then apply the hash function. This output altogether is appended at the end of another round. So this is the key XOR with OPAD, and then enter the hash again. So kind of like mixed with the message in two different, in a nested fashion. It's nested. So this key mixed with the message enter the hash in the first in the nested round. Okay, inner round, and then altogether it will enter again. So this is called HMAC. So this HMAC does not specify any hash algorithms. You can use any hash algorithms for this hash. Can be MD5, can be SHA-1, right? And SHA-256, can be anything. And then this is also the standard as well. So that's what we use for digital signature. So digital signature is used this way. Okay. If you want to use a hash-based MAC, message authentication. Oh, I'm sorry, not digital signature. The digital signatures, you apply the hash function directly and then you sign the private key. But if it's used in a symmetric case, okay, if you want to use keyed hash as message authentication code, then you use HMAC. That's it. So that's a hash, okay, HMAC. Okay. these are the two papers written by Wang Xiaoyun. You guys can take a look. Okay. So Wang Xiaoyun, basically, she found a way to produce collision. So in other words, you can use that, you can exploit that to produce valid signatures. Okay, chosen plan has attack. Okay. So that's also collision attacks. Okay. So far that's the weakest link of. That's the weakest link. Okay, so we're done, pretty much done with the hash function. Now, our next topic is elliptic curve photography. This is a relatively new algorithm. I'll post this. I probably haven't posted this online, so I'll do that later today. Okay, so let me introduce this. So the elliptic curve in Chinese, it's 椭圆函数. Okay, so we're going to look at this. Okay. First, let's talk about it. It's a joke. The French writer, the great French writer, said the Holy Roman Empire is neither holy nor Roman nor an empire. Yeah, that's one of the famous quotes by French writer Voltaire. Yeah. So it's neither holy because it's it's a regime, so it's definitely not holy, nor Roman because it's not. They're Germans actually. So if you guys know what the Holy Roman Empire was, it's pretty much Germany. Germany, Austria. That's the Holy Roman Empire. And then it's not an empire. Because it's almost like a European Union. It's kind of like a club. And then there's no capital, even though there are some capitals. And then the ruler, there are. You can regard it as a collection of small kingdoms, okay, and then some of the cities they have the power to elect the emperor. So the emperor is more like nominal. There's really not a highly unified country, so it's not an empire either. Okay. What's funny was the elliptic curve crypto system is neither related to ellipses nor it is itself a crypto system. So this name is very misleading. Elliptic curve crypto system. Okay. So let me explain what's the relationship between elliptic curve crypto system and ellipses. So we know what's ellipsis. First, we look at, we can use elementary calculus to calculate the arc length of an ellipse. Okay, so the ellipse is this, the arc length is this. An integration, the arc length of a half ellipse is this. Okay, no big deal. Now, we do a change of variable. Okay, if we set k squared to be this, change variable, then the arc length becomes this. So you have this. Okay. Initially, mathematicians were doing something called elliptic integral. This is elliptic integral. And then we'll do another change of variables. The arc length is this, and then we have a relationship with this. Okay. Y squared equals this. Okay. Y. Okay. So elliptic integral. So what's funny was now we will have a really big jump.
extremely big. So this is a quartic equation. That means the degree is 4. Okay? That's because of elliptic integral. Because of you change your variables, you have a square root there, and then you have square inside. So generally, you have a equation of degree 4. What's interesting is that the elliptic, so this is called an elliptic curve. However, the definition says, now this is a big jump. If y squared is equal to mx, which is quartic in x, we can call it elliptic curve. That should be okay. But what's funny was they also call the case where it's a cubic, degree 3. And it's also called elliptic curve. And then actually, you guys may guess, what is the major elliptic curve? Is it degree 3 or degree 4? Let me tell you, it's actually degree 3. It's a cubic. So you're doing all this shit, and then now you tell me that y squared equal to cubic. This is called elliptic curve. It's elliptic curve. Any cubic cone, any elliptic stuff related to cubic terms. Are you kidding me? So this is like really, really big jump. I would say there's nothing to do with ellipsis. 它椭圆函数，它竟然会跟三次方有关。你告诉我椭圆什么时候会出现三次方？有吗？不管是高中学解析几何啊，什么抛物线、椭圆双曲线啊，这些东西会有三次项出现吗？很奇怪，对不对？它就被称之为 elliptic curve， 所以这真的是一件非常奇怪的事。然后我觉得更奇怪的是，很多地方都会听到 elliptic curve 这个名称，物理也有用到。然后还有一些，比方说我们之前有讲这个 primality test， 有 elliptic curve primality test， 这个也跟都没关系。基本上我可以跟各位讲，同学只要听到 elliptic curve 这个字，不管在任何一个相关的领域你要先确定一下这到底是什么东西，因为只听到 elliptic curve 这个名词没有办法给你任何 information， 完全要看它的内涵是什么。这个内涵常常很怪。Anyway, we'll explain. Number one, the elliptic curve crypto system itself, ECC, is not a crypto system. It basically uses the so-called elliptic curve that I mentioned earlier to define the group. It's just a group, okay? And then we use this group to perform the discrete log, generalized discrete log problem, okay? And as we said earlier, there are many algorithms that's related to the general discrete log problems, like Elgamal, like DSA, like Diffie-Hellman, right? These are related to the discrete log problem. All these algorithms you can actually apply. You can apply this elliptic group to these algorithms. So altogether, if you combine those, they are a crypto system. So it's not that the elliptic curve is a crypto system. No, it's just a group. And then this is a group studied by mathematicians. If you apply this group to these algorithms, that's a complete crypto system. So that is why you may have, for example, elliptic curve DSA, okay? Or you can have elliptic curve Diffie-Hellman key exchange. We will explain later. Elliptic curve Elgamal encryption algorithms, things like that. But elliptic curve alone is not a crypto system. And also, here we use ECC in this lecture, we use ECC to represent elliptic curve crypto system. Because unfortunately, there's another ECC. There's something called error correcting code. In coding theory, we have error correcting code. That's also called ECC. Okay. So if two collisions of acronyms, we have MAC. There's a collision. There's ECC. There's another collision. Just make sure. Okay. So we can use the elliptic curve on all discrete log-based problems, including Diffie-Hellman, Elgamal, Elgamal signature DSA,
so on and so forth. Okay. And then because there are no good attacks on the discrete log problems, and then there's no good attacks on the elliptic curve based algorithm either. And then they're even less because people really don't understand what this group behaves. It's defined in a very counterintuitive fashion. I'll explain. It's kind of really weird. Yeah. So because this group behaves, we can say that behaves in a weird manner, or because people are not familiar with those things. Mathematicians are way more familiar with, for example, factorization than elliptic curve stuff, because this is designed using algebraic geometry, algebraic geometrical concept. Okay. Actually, in math, there's a big branch called algebraic geometry. Algebraic geometry. Okay. It's geometry using algebraic measure. So this is an adjective. Algebraic is adjective. Geometry is the name. So algebraic geometry is geometry. Okay? And there's also another one called geometric algebra as well. This is geometric algebra. That's different. Totally different. Okay? There's a geometric algebra. So this is totally different. So they're using this. Actually, there's similar things. 我也知道，像有一种东西叫物理化学，对不对？物理化学其实化学不是物理，化学物理才是物理，因为物理是形容词。知道哈？就像阳明交大说哈，人家阳明交大应该是交大，因为这世界上有很多个交大。好，有上海交大，有西安交大，所以我们也有阳明交大，所以阳明交大是交大。事实上，当初呢，清华大学也很想要跟阳明大学合并。我们其实比交大更早去接触阳明。好，然后呢，都谈好了，最后就有一个问题，合并之后要叫什么？我们清华大学非常坚持，必须要叫清华大学，没有别的选项，因为清华大学才是最正宗的，对不对？所以这个是后来交大半路杀出来，他说：“哎，没关系，你不要跟清大谈，好，我们可以呢把你阳明加上去，而且我们还可以把阳明放前面，叫做阳明交大，没有叫做那个交通阳明大学，没有。就阳明一听，哇，不但名字可以有阳明，他终于可以保存阳明这个血脉，而且还可以放前面呢。就那阳明他就回去。”他们就跟校会研究，哇，交大给我们条件真好。那交大自己对内说，我们虽然给他们前面，可是呢，其实阳明交大是交大的意思，我们可能没有把主权让出去，没有说阳明交大是阳明哦，因为阳明是形容词，交大才是名词。这世界上这么多个交大，这世界上可能没有那么多个阳明，对不对？这个意思，就两边都说得通，两边都可以各自对自己的支持者的。说得通，都有一种说法，最后这个事就成了，然后我们就破局了就是这个事实上就是这样的事情，所以名正言就顺，这种两种解释方法这就是一个政治上巧妙就在这个地方，只要有两种说法，你换一个说法，可能就可以把它引导成那个方向去。So it's a joke. Anyway, this is elliptic curve. As we can see that it's a little weird. The elliptic curve, basically it's a curve like this. We have x and y. So the y squared equal to a cubic term of x. Okay. The cubic term, we can have x cubed plus some x squared plus some linear term and constant. So because we have this, okay, something like this, generally speaking, okay, first thing, we can apply
change of variable to kill this term, a. So in other words, we can always kill this one by introducing a new variable, so to eliminate this. So we can actually set this a to be 1, for easier calculation. In other words, moreover, we can also kill this term as well. 数学上有个叫配方法，可以配方把这个配掉。大家如果知道像那个2次式，我们可以用配方，希腊就是用配方，然后把2次解掉。我们可以配方，就你把这 x 呢，你变成一个 x 再加上什么东西，这样3次方这样做个变数，你去调整这个参数，可以把这个 b 给弄掉，就可以把它弄掉，零越多越好。So actually, there's a way. Okay, we can apply some translation. So we translate this x, okay, by replacing x plus something, okay. Then we have a cubic term mixed with lots of stuff. Then we'll be, let's say we'll have a b c d. Let's say g, okay, x plus g, for example, and we can choose this g appropriately. That this g, here we know that in this cubic term we'll produce some square terms. Also here we'll produce some square terms. Okay, they both contain the variable g. Okay, we can adjust this g so that the square terms they cancel each other. 这个叫做配方法. Okay, so that is why we can also kill this term. The remaining linear term and constant term, we cannot do anything more. These are 2 tricks. So this is the easiest version of the elliptic curve. So we have a cubic term, and then we have a linear term and constant term. There's nothing more we can do. That's the easiest way. And then this x goes from 0 to infinity. Okay? But this y, okay, this y is symmetric. So if you have, let's say you substitute some x, for example, x is equal to 2, okay? If x is equal to 2, you plug in this number 2, you get some number, and then this y squared is equal to this number. So y will be plus minus this square root of 12. That is why, for example, you plug in the number x, and then you have plus and minus. It's symmetric. And then if x is a negative number, and it's a very big negative number, then this whole term will be negative. If it's negative, then you don't have any roots at all. So you don't have any roots at all. Okay, that's it. So that's what it looks like this. Sometimes it may look like this. Sometimes it may look like this. So sometimes you have one piece. In other times you have 2 pieces. That's because, let's say you have something like this. Okay? I'll just give you guys some examples. Let's assume that the cubic terms can be factorized this way. Okay. Now, depending on where x is, you have different. The curve will look very different. For example, if here we have 3 roots, okay, x is 1, and then 2, and then 3, right? If x is less than 1 here, x is like this, okay? Then, if it's less than 1, then these 3 parentheses, you have a negative sign here. This pair of parentheses will contribute a negative sign, and then another negative sign, another negative sign. So altogether, it contributes 3 negative signs. So that'll be a negative number, which means no root at all. So nothing, like this. Okay? And then, let's see if the x sits between 1 and 2. Okay? If x is between 1 and 2, then you have a positive number here. You have a positive number, but these 2, you have 2 negative numbers. So altogether, you have a positive number. So you have some value. when you have a value, you have plus and minus because you're actually calculating the square root of y, so you have plus and minus. So that's between 1 and 2. And also, if x sits between 2 and 3, then you have 2 positive and 1 negative. So you have a negative value, then you have no solution at all. Okay? And finally, if it's bigger than 3, okay, you have 2 solutions. So the curve may look like this. Depending on these values, A and B, you may have 1 piece or 2 pieces. Okay. Sometimes you may have degenerated case. The degenerate case is something like this. You may have something like this. Degenerate case. They actually touch each other. It's possible. Okay. This is a degenerate case. But anyway, let's just think about it this way. Okay, so the elliptic curve will look like this. Okay. And then if a degenerate case like this, if it happens, you can actually look at it, you can look at the这个二次式我们有所谓的判别式有的时候判别式就是有没有解啊什么的这个叫那个叫判别式，三次式也有判别式，这叫判别式这个好像叫做 determinant 是不是 ？Okay, so for quadratic equations you have a determinant. So the determinant that's this. This gives you an information whether or not you have solutions. Okay, and how many solutions you have. If it's equal to 0, that means you have 1 solution. If it's less than 0, you have no solution. If it's bigger than 0, you have 2 solutions. For cubic equations, we also have similar things. So the determinant is this. Okay, and then if it's 0, that means you have at some point you have multiplicity too. Okay, you have multiplicity. That's something like these 2 pieces actually touch each other. This type of elliptic curve is a degenerate case, and we cannot use, okay, because it contains repeated factors. Okay. But anyway, this type of elliptic curves, okay, if the determinant is 0, then we cannot use. We have to avoid that case. So we have to assume that this is not 0. Okay. So we can only use either like this one with 1 piece or the other one, I say we have 2 pieces. Okay. Now we're going to define a group. This group is the definition is a little bit I should say is quite counterintuitive. 等下我们要定义一个群这个群的定义有一点点抽象，然后有点怪，这样子，不太直观，这是很不直观的东西等下我们再来讲。Okay. Now, okay, so group. If you guys remember that, what forms a group? You have a set, and then you also have an operation. You have to satisfy 4 rules. 4 rules. Closure, associativity, identity inverse. 4 rules. It's a group. So first, we have to tell you guys what the set is. Okay. So the basic elements of a group is first you have to introduce a set, and then the operations. Okay. And then 4 requirements. Number 1, closure, associativity, identity, inverse. So you have to have a set G, okay, and some operation. Both of them are a little bit weird. What's G? The set consists of all points on the curve plus an imaginary point. So that point you can't see. That's a little counterintuitive, right? 好，所以这个 group 的这个是什么？曲线上的点就是它的 element。
points on the curve plus an imaginary point. We can't see. And we call that point the point at infinity. And it's denoted by big O and point at infinity. 好，是这样。好，很怪哈。Now, operations. Want to define an operation. Okay. Give me 2 points. Give me 2 elements in the group P and Q, okay? 2 points on the group. Okay. First, we draw a line. Okay. And this line will intersect another point. This line will intersect another point because if you do a change of variable, it's going to be third. You will solve a system of 2 equations. One of them is the elliptic curve equation, which is cubic equation. And then you have another two solutions. And as we can see that a cubic equation, okay, in real numbers, either has 1 solution or it has 3 solutions. There's nothing like you have 2 solutions. The reason is all these solutions, if there's no solution, that means their solution is in the complex number. But the complex numbers, they always come in pairs. They're conjugates. So if you have 2 solutions and then you're not degenerate case, that means you must have a 3rd solution. So we'll intersect at the 3rd point. What's weird is that this is not the definition of addition, of the operation. You actually perform the mirror point. The mirror point is considered the addition. 这就有点怪哈。我们再讲好。定这个我们要去定义这个运算。好，你先拿一个点 G， 挑一个 P 出来，再挑一点Q。好，我们要定义这 P 跟 Q 的运算，对不对？怎么定义？这是2个曲线上的点，好，就画一条线。那画一条线呢，它会交第3个点。如果不是degenerate case的话，它交第3个点。因为呢，我们知道你用这个变数变换，你把它这条线的方式带到这个曲线里面，就是解第3个值嘛。那解第3个值，因为它这个系数都是实数的，那你先解个3次方程式，你就只有2种 case， 你要么1个解，要么3个解，这样子还是因为你3次方程式哈，你如果没有重根的情形，一次要么1个解，要么3个解，因为你如果说都有解，就3个解嘛，对不对？那如果说是你中间有一个是负数的，就是你没有解，你就解释负数。但是它负数它一定是成对出现，它一定是共2同时出现的。你不可能说你有一个负数，你解出来，那2个负数不共2，这是不可能的哈。所以你一定共2出现，所以你只要出现一个负数根就是2个了，那时候就只有1个解。那现在你已经2个解了嘛，对不对？那是代表一定有第3个解，所以你一定会交第3个点。怪的就是说，这第3个点并不是它定义，它是再把它做一次 mirror， 这才是这个 R 叫做定义成 P 跟 Q。That is a little weird. So that's the definition. Well, in some case, you may not intersect the 3rd point, like this. You have a point here. Let's say this is a point. This is another point. And then you draw a line. It really doesn't intersect at any point because in this case you have multiple roots. That's kind of like a degenerate case. Well, if that happens, then the imaginary points will be used. So we think they actually intersect at infinity. You have to use your imagination in this case. So in that case, we directly define their sum, the operation to be the point at infinity. Now, if one of the points is an ordinary point on the curve, the other point is the point at infinity, then you cannot draw a line, right? Okay. Then we define the operation to be that point itself. So basically, we treat the point at infinity as the identity. 就是这样。所以我刚才讲的曲线上面的点，再加上一个想象中的无穷远点，这就是你的 group 里面的这个元素，对不对？好，那万一你真的交不到第3个点，就像这样垂直线，那没关系，直接规定它等于 point at infinity， 用想象。然后呢？然后如果说你今天有某一个点再加另外一个点，对不对？其中一个点是 point at infinity 的话， 那么就是另外一个点啊，就这样子，没有什么啊，直接规定啊，就直接规定。然后呢，两个都是 point and infinity，point and infinity 加 point and infinity 也是 point and infinity， 就这样子，这就强行规定，这样就可以变成一个 group 了啊，这个就很怪，对不对？这基本上是这样子。那这个呢，我们可以看一下，它其实满足了哈很多条。Let's check these rules. Okay, closure. It actually covers everything. If you give me any point, whether it's point at infinity or not, you always end up with another point. So closure is okay. And the identity, we can regard as point at infinity as identity. So that is okay. What about inverse? For any point, you want to have an inverse. Yeah, because for any point, give me any point here. The inverse is simply the mirror point. Because, when any point at its inverse, it's a point at infinity, so its inverse exists. So this is okay. Identity is okay. It's imaginary, but it's okay. And also, not just this one. We have an additional one. Commutativity. In other words, P plus Q and Q plus P are the same. The reason is, no matter whether it's P operation Q or Q operation P, you are just drawing a line passing P and Q. So it makes no difference. The result makes no difference in P operation Q or Q operation P. So they're the same. So it's commutative. That's the reason why this is actually an abelian group. And then for abelian groups, we can use plus. You use the plus sign instead of the multiplication sign. So we simply call P plus Q, Q plus P. 这就为什么用加法。Okay. The only problem is that this we're not sure associativity. And actually, it's extremely, I would say, it's extremely difficult to show that associativity hold, and it's also extremely non-trivial at all. Let's take a look. Okay? So let's see. We have two cases. Okay, so either this case or another case. Maybe we can take a look at this case anyway. This case. To show that associativity actually works, you need to have 3 points. Right? 3 points. For P, Q, and R. Let's say you have a P, okay, and then Q. Okay. P. Let's say you have Q, and then R. Okay. You tell me first you draw P, get Q. Okay, and then you have this point, right? So this is P plus Q. And then you draw with another R. You draw with R or something, and then that's another Q, and that's another point. I didn't draw it very well. Anyway, maybe this is P plus Q plus R. You're telling me that you draw this line PQ first, and then you do this again is equal to this, and then it's the same as, for example, you draw Q and R. But Q is here, R is here. You draw Q and R. It's like you draw it somewhere else. It's really non-trivial to show. Okay. I was trying to represent this as an equation. We know this is an equation. I was trying to represent everything as equation and find the answer. The problem is we're dealing with not just quadratic. We deal with cubic terms. For cubic terms, anything you do with cubic, the cubic and do a cubic, you have you have like more than 10 terms. And then a lot of times these solutions, they don't have closed form. So I was trying to calculate, this using brute force, but I couldn't do it. So if you guys can do that, please let me know. I will definitely give you a lot of bonus points. 我想要证明这个 associativity 结合律成立，那我就用暴力法3个点单去算。我算了大概 7、8张计算值我算不下去，所以我个人算不出来，最后我放弃了。有同学算得出来，马上跟我说，绝对给你 bonus 啊，因为这个很难算，我最后就是放弃了，想要暴力法强行证明算不出来。associative 非常困难，这个要用代数几何的理论，其实可以很容易理解，但是如果要暴力计算真的很难，而且3次方这种东西你也没有什么，你公式很丑，然后里面又根号，外面又3次方，我真的算不下去。Let's stop here. Yeah, we'll continue next time.